Welcome to Knowledge Targeting, Part 14, Synthetic Telepathy and the Brain-Machine Interface. Over the next 2 hours, we follow a single document from a checkable claim about a real defense research program to a claim that runs far past it. Along the way, we will build something useful, a method for sorting any brain-machine interface story you meet into what has been demonstrated, what has merely been funded or filed, and what is only asserted. That is Robert Asher, a scientist at Sandia National Laboratories, speaking in June 2002. Sandia is not a fringe outfit. It is one of America's nuclear weapons engineering laboratories, run for the Department of Energy. 2 months after Asher said that, DARPA, the Pentagon's research agency, confirmed the program publicly and on the record. In this literature, that is rare. A checkable claim, checked and still standing. We start where the ground is solid. Knowledge Targeting is a 50-part documentary series from TI One Voice, written by Stefan van der AA. Each part takes one document, one case, or one mechanism and works through it slowly in public. The rule never changes. Documented fact is named as documented fact. Contested claim is named as contested claim. Where the evidence runs out, we say so out loud rather than gliding quietly over the seam. This hour follows that rule exactly. This is part 14 of 50. Part 13, the microwave auditory effect, voices in the head, examined a genuinely demonstrated phenomenon, sound produced inside the head by pulsed microwaves, published and replicated. Part 15, remote neural monitoring, reading the mind from a distance, takes up the claim that brains can be read remotely. This episode sits between them, and it is the hinge. What can a brain-machine interface actually do, and with what hardware? Everything behind this episode lives on TI One Voice at one.witisk.org. It holds the evidence library where targeted people log incidents in a structured form, the knowledge base several thousand documents deep, which is what these episodes are built from, the community wall, and the One Voice declaration. You do not need an account to watch. You do need one to file evidence that other people can later count. We also run TITV, a live stream for targeted individuals, 24 hours a day, at meet.witisk.org, under public, TITV. Every part of this series has a written companion article on the platform, carrying the same citations you will hear spoken, so you can check a name, a year, or a journal at your own pace. If a claim in this hour matters to you, read the article and follow the source. This episode was assembled by retrieval over the TI One Voice knowledge base, a search across the whole document collection, feeding a draft that a human then checks line by line. Its anchor is a compiled document cataloged as Knowledge Base 19, known internally as Mind Weapon. We draw on its sections 2, 16, and 20. Where the knowledge base is thin or where a source cannot be verified, we will name that too. 3 registers run through this hour, and they must never blur. Demonstrated means a named study, named authors, a year, a journal. Filed means a patent, a contract, or a research proposal, proof that a document exists and nothing more. Claimed means testimony and inference, something asserted about a person who did not consent, with no measurement behind it. All 3 are worth discussing. Only one of them is evidence of a capability. Here is the decisive fact of this episode, and it will be repeated. Every brain-machine interface that has actually worked required hardware inside the skull or pressed against the scalp. Every one required days or weeks of calibration tuned to one specific person. And every one required a volunteer who wanted the system to succeed. Remote, contactless, uncalibrated operation on an unwilling person is not a near neighbor of that. It is a different order of thing. Here is the hour, running deliberately from firm ground to soft. First, the Sandia memo. Then what DARPA actually built, from a 2002 announcement to a robotic arm moved by thought. Then the leap the document itself makes, from muscle commands to emotion and will. Then the Army's $4 million synthetic telepathy grant. Then the brain transmitter claim and the patents behind it. And finally, the method for sorting all of it. A word to anyone watching who believes they are being targeted. We will not diagnose you, and we will not tell you what is or is not happening in your life. We do not have that standing. What we can offer is precision because precision is protective. A vague claim can be dismissed in one sentence. A dated, sourced, carefully limited one cannot. The declaration guide in our knowledge base puts the practical part very plainly. So Chapter 1. The signal that checked out. A named scientist at a named laboratory on a dated occasion, describing a defense research program that we can go and verify against the public record. That combination is unusual in this material, and it is the reason this document earns an hour of careful attention rather than a shrug. Before we test the sentence itself, we need to know who spoke it and where he worked. Sandia National Laboratories sits outside Albuquerque, New Mexico, on Kirtland Air Force Base, with a second site in Livermore, California. It is a Department of Energy laboratory, and its historic job is the engineering of everything in a nuclear weapon except the physics package. The arming, the safing, the electronics. Its work now runs well beyond weapons, into energy, computing, and broader security research. Robert Asher was a scientist there, working on neural interface questions. Read Asher's sentence carefully, because its modesty is the point. When you decide to move, the command leaves your motor cortex, travels down a nerve, crosses the junction into muscle, and only then produces motion. That takes time on the order of tens to a few hundred milliseconds. A brain-machine interface taps the command before the muscle. That is all he claims. Signals going out of a brain by wire into a machine. So the demonstrated path runs one way, and it runs on hardware. Neurons in the motor cortex fire. An electrode array sitting in the tissue picks up that firing. A decoder, trained on this individual person over hours or days, maps the pattern onto an intended direction. A cursor moves or a robotic arm does. Nothing in that chain reads a thought in words, and nothing in it happens without physical contact. The idea did not appear in 2002. In 1969, Eberhard Fetz showed in the journal Science that a monkey could learn to control the firing rate of a single cortical neuron. In 1998, Philip Kennedy and Roy Bakke reported the first implanted interface restoring output in a paralyzed patient. In the year 2000, Miguel Nicolelis's team at Duke published monkeys driving a robot arm in Nature. This is what such an interface physically is. The Utah array is a square of silicon about 4 millimeters on a side, carrying 100 needles roughly a millimeter long, pushed into the surface of the cortex. It requires a craniotomy, a surgeon opening the skull. Wires run from the array to a metal connector bolted through the scalp. Infection risk, signal decay, and repeated recalibration are ordinary features of that arrangement. 96. That is the number of recording channels wired on the array implanted in the first BrainGate participant, a young man paralyzed from the neck down, reported by Lee Hochberg and colleagues in the journal Nature in 2006. 96 tiny windows onto a few square millimeters of one cortex. That achievement is real and it is remarkable. It is also, physically, about as far from action at a distance as you can get. Put the two columns side by side and the distance is not rhetorical, it is measurable. On the left, what has been shown. Contact hardware, a consenting participant, calibration fitted to that person, a wired laboratory, a decoded movement intention. On the right, what is claimed. No contact, no calibration, no consent at range and speech arriving in both directions. And note the trap. Absence of a published capability is not evidence of a hidden one. Hold that gap in mind because we are about to cross the strongest part of the case. 2 months after Asher spoke, DARPA announced its brain-machine interfaces program in public, and the money went to real laboratories, Duke University among them. In the next stretch, we follow that announcement into the contracts, back into the animal experiments that preceded it, and forward into the trial that put a robotic arm under human thought. So we have our anchor document and we have its opening sentence. Before we test the claim itself, we test the person who made it, because in this literature a name is usually where the checking has to start. Robert Asher was, in June 2002, a working scientist employed by Sandia National Laboratories. Who he was and what that institution actually does decides how much weight that single sentence can carry. Public records place Asher inside Sandia's Sensor and Signal Processing Research Directorate. That is not a neuroscience laboratory. It is an engineering shop, radar systems, electromagnetic sensing platforms, telemetry receivers, and the processing chains that turn raw electrical noise into usable data. His publication record is sparse by academic standards, and it points one way: defense sensor integration, measuring the physical world and interpreting that measurement in real time. That background shapes how we read his sentence. Strip away the hardware and one problem runs through all of it, pulling a faint signal out of a much louder background. Noise rejection, bandwidth, electrode design, amplifier sensitivity, signal-to-noise ratio, the algorithms that tell a genuine event from a random fluctuation. That is a discipline, and it is the same discipline whether the faint signal comes from a missile telemetry link, a radar return, or a firing neuron. Asher spent a career there. So his expertise is genuinely adjacent to brain-machine interface work. Decoding a neural signal is, at bottom, a weak signal problem. But adjacency is not authority. A man who can build the amplifier is not thereby an expert on what the brain is doing, and the knowledge base entry on Asher is careful about this. His presentation has been read as evidence of a mind control program, though he himself made no such claim. Hear what that sentence is and is not. It is a description of a decoding problem. Take the brain's own motor planning signal, read it, and act on it before the muscle moves. That is exactly the class of problem his career trained him to recognize. It says nothing about reading a private thought, nothing about distance, and nothing about doing any of it to somebody who has not agreed to take part. Set the demonstrated register beside it now, because we will use it all hour. In 2006, in the journal Nature, Lee Hochberg and colleagues reported the BrainGate trial, a 96-electrode silicon array implanted in the motor cortex of a paralyzed man, letting him move a cursor and open a prosthetic hand. Real, published, replicated. Also surgical, wired, calibrated session by session, and entirely dependent on a willing patient. That is the decisive fact of this episode, and I will repeat it. Every demonstrated brain-machine interface needs invasive or contact hardware, lengthy per-subject calibration, and a cooperating participant. Remote, contactless, covert operation on an unwilling person is not the next step along that road. It is a different claim by orders of magnitude. And note carefully what the gap does not prove. The absence of a published remote system is not evidence of a secret one. Which brings us to the institution standing behind the name, because half the weight of Asher's sentence comes from where he worked. When a claim in this literature cites a laboratory, the honest question is always the same. Is that a real place doing real work with real relevant expertise, or a name borrowed to lend authority? In this case, the answer is unusually clear, and it points both ways at once. Sandia National Laboratories is not a fringe outfit. It is one of the United States Department of Energy's 3 nuclear weapons engineering laboratories, alongside Los Alamos and Lawrence Livermore, founded in 1949 on what was then Kirtland Air Force Base in Albuquerque, New Mexico. The knowledge base entry records its principal sites at Albuquerque and Livermore, California, and its responsibilities in nuclear weapons design, energy security, and national defense. 70-odd years of engineering in one place. This management has changed hands more than once, and the names are worth hearing. The University of California ran it first, then AT&T Bell Laboratories. From 1993, Sandia Corporation, a wholly owned subsidiary of Lockheed Martin. Since 2017, National Technology and Engineering Solutions of Sandia, a Honeywell subsidiary. Different owners, one continuous mission, and by 2002 an accumulated depth of engineering that very few institutions anywhere could match. The founding mission was stark. Sandia engineers the non-nuclear components of the American nuclear arsenal, the arming, fusing, firing, and delivery systems that turn a physics package into a functional, deliverable, reliable weapon. That is unglamorous work of extraordinary precision, and it demanded a particular set of skills. Materials science at extreme conditions, environmental sensing, telemetry, signal processing, and the integration of complicated hardware that has to work first time, every time. Those skills radiated outward over decades into a much wider portfolio: radar and electromagnetic sensing, directed energy experimentation, microelectronics, microelectromechanical systems, and, critically for us, the design of sensors that detect extremely weak physical signals. The knowledge base entry on Kirtland notes Sandia's work on advanced sensors and electronics sitting right alongside the base. That last competency is the bridge between a nuclear weapons laboratory and the brain-machine interface world. It is a real bridge and a narrow one. Consider the numbers that make this hard. A scalp electrode picks up perhaps 10 to 100 millionths of a volt, smeared through skull, scalp, and hair, summed from millions of neurons at once. An implanted array sits micrometers from individual cells and hears them directly. Both are contact measurements. Both need amplifiers pressed against or inside the head. Nothing in that physics gets easier by moving the sensor across a room. The knowledge base entry on synthetic telepathy as a research term puts the position plainly. Current systems, it says, require direct contact sensors, e.g. caps, muscle electrodes, extensive user training, controlled environments, and they achieve only limited vocabulary recognition. No peer-reviewed research has demonstrated remote, non-consensual, or real-time decoding of complex private thought at a distance. That is the published state of the art, stated by our own reference library. But the credibility cuts both ways, and honesty requires saying so. National laboratories compete for congressional funding, Pentagon contracts, and graduate talent. A laboratory that can describe itself as working on the interface between the warfighter and the battlespace is positioning itself for relevance in a funding environment that rewards exactly that language. Enthusiasm is not fraud. It is, though, a pressure on how research gets described in public, and we should hold it in mind. Now to the list itself. Right after naming Asher, the document says what the program is supposedly for, and the list is worth reading slowly because it travels a very long way in a single breath. Listen for the moment the register shifts. Control of aircraft, reasonable. Learning and training. Automobile control. Air traffic control. Then decision-making. Then remote sensing of stress. And then, at the end, one plainly dissonant word. Entertainment. 7 items, and they do not belong in the same category. The first 4 are about acting on the world, steering something, supervising something, training someone. The 5th and 6th are about the inside of a person, what they have decided, what they are feeling. The 7th is a consumer product. Sorting an enthusiastic list item by item, rather than swallowing or rejecting it whole, is the habit this episode is really teaching. Take the first item seriously because it is serious. By 2002, military aircraft already flew by wire. A pilot's hand on the stick sent an electrical signal to a flight computer, which commanded the control surfaces. Workload monitoring, physiological sensors watching a pilot's fatigue and stress, was an active research area across several Air Force laboratories. Reading an intended bank or throttle command straight from motor cortex is a coherent, fundable idea. Now the second half of the list, and here the engineering problem changes in kind, not merely in degree. A reach, a cursor movement, a prosthetic squeeze. Those are motor intentions, generated by populations in motor and premotor cortex whose firing patterns have been mapped across decades of animal and human work. A stress state, a decision, an emotion has no single agreed neural signature, no dedicated region, and no decoder that generalizes between people. None of that makes the list dishonest. It means its items sit at wildly different points on one continuum, and each deserves the same question. How much of this has actually been built? Carry that habit into every chapter that follows. And it raises the question the next chapter answers first. Why begin an entire episode with one quoted sentence? Because it names a person, an institution, and a date. 3 checkable things. So why begin an entire episode with a single sentence from a single scientist, rather than with the sweeping story the document goes on to tell? The answer is methodological. In a literature where claims multiply faster than citations, a claim naming 3 specific things, a person, an institution, and a date, is a claim that can, in principle, be independently checked. Everything else in this episode will be measured against that standard. Robert Asher is a real name, attached to a real employment record at a Real National Laboratory. June 2002 is a specific month. And the sentence itself, that DARPA has a brain-machine interface program about to start, is a proposition with a truth value. Either such a program existed, was announced, or was funded around that window, or it was not. There is no third option and no room for interpretation. Those 3 properties are what separate a checkable anchor from an uncheckable narrative. A narrative can be vast, detailed, and internally consistent, and still offer nothing a stranger could go and verify. An anchor is smaller, plainer, and infinitely more useful because it can fail. That is the whole point. A claim that cannot fail cannot be evidence, however powerfully it is told, and however many pages are built on top of it. Here is the sentence in full, and notice how little it actually says. It does not mention remote thought transmission. It does not mention voices or targeting or unwilling subjects. It says that a defense research agency was about to begin work on brain-machine interfaces. That is a modest, bounded, verifiable statement, and the modesty is precisely why it survives scrutiny when the sprawling document built around it does not. Keep hold of that distinction. The checkability principle extends far beyond this one document. Throughout this series, we apply the same test to every source. Can any part of the claim be verified against something that is not itself part of the contested literature? The knowledge base entry on synthetic telepathy in TI usage is blunt about the result. No documented, independently verified cases exist in the public record. Where that is true, we will say so. So how does Asher's sentence fare? Remarkably well. 2 months after he was quoted, DARPA made its brain-machine interface program public. On the 20th of August, 2002, press outlets including Science Daily reported that the Defense Advanced Research Projects Agency would support the development of human brain-machine interfaces through a multi-year contract centered at Duke University. The anchor held a real program at a real university in the window the quote described. This matters, and it is worth being precise about why. The program was genuine, publicly announced, and independently reported by outlets with no stake in the targeting literature. The knowledge base entry on the early DARPA brain-machine interface program notes that it is frequently cited in the TI community as a documented origin point, and that synthetic telepathy, where it was discussed at all, remained firmly in the realm of speculation. The announcement named 2 explicit goals. First, neuroprosthetic limbs that paralyzed people could control with their own neural signals, bypassing damaged spinal pathways. Second, brain-controlled robotic systems the announcement called neurorobots, machines moved by thought rather than by joystick. Both goals are about sending commands out of a cooperating brain. Neither is about putting anything into one. In its explicit scope, the program was dramatically narrower than the sweeping list attached to Asher's quote. The Duke contract went to a research group led by Miguel Nicolis, a Brazilian-born neuroscientist who had already spent more than a decade on brain-machine interfaces. He was not an obscure figure, and the award was not a surprise. 2 years earlier, Nicole Leese and his colleagues had produced the demonstration that made the whole field fundable. The experiment every later claim about thought-controlled machines quietly leans on, whether or not it names it. In 2000, in a paper published in Nature, a monkey with an implanted electrode array in its motor cortex controlled a robotic arm that reached for a piece of food. The animal did not move its own biological arm at all. The firing patterns of its motor neurons were recorded, decoded, and turned into motion in real time. It is still one of the most important experiments in modern neuroscience. The experiment silenced a specific class of skepticism. Critics had argued that the signals would degrade too quickly, that the decoding problem was computationally intractable, or that the brain would simply stop producing usable patterns once the arm stopped listening to them. None of those fears materialized. The monkey adapted. The algorithm adapted. The arm moved. That is a genuine, demonstrated, peer-reviewed capability, and nothing in this episode takes it away. But notice what the experiment also required, because this is the decisive fact of the episode. The monkey was implanted surgically. The electrodes were invasive, penetrating the cortical surface. The recording equipment was physically wired to its skull. The work took place in a shielded laboratory, after months of training, with extensive calibration and a dedicated team managing signal acquisition and decoder tuning, live while the animal worked. Every one of those conditions is contact hardware. The signal being read was a motor intention signal, a reach to a point in space, a firing pattern decades of primate neurophysiology had already mapped. This was not thought reading in any general sense. It was a narrow, spectacular instance of motor decoding. The knowledge base states the position bluntly. No system has been demonstrated to achieve the level of control described in targeted individual accounts. Confusing the two is a category error. The 2002 program did not emerge from a vacuum, and knowing its lineage tells you how fast this technology has actually moved. The term brain-computer interface was coined, as far as the published record shows, by Jacques Vidal, a computer science professor at UCLA, in a 1973 paper titled Toward Direct Brain-Computer Communication. The knowledge base entry on brain-computer interfaces dates the modern field to exactly that paper. Vidal proposed using scalp-recorded EEG, electrodes on the head, to let an operator communicate with a computer without speech, gesture, or keyboard. The knowledge base entry on synthetic telepathy names the two obstacles that have dogged that idea ever since. EEG signals are noisy and low in spatial resolution, and the decoding algorithms need extensive training for each individual user, because neural patterns differ from person to person. Remember that second obstacle. Set the dates side by side and the pace becomes clear. The knowledge base entry on neural signals puts it plainly. For most of the 20th century, recording brain activity stayed a clinical and research tool, with limited ability to decode specific mental content. 3 decades separate the coining of the term from the first funded military contract, and every step between was incremental, invasive, and hard-won. This field crawled. It did not leap. The foundational result came earlier still. Eberhard Fetz, at the University of Washington, showed in the late 1960s and early 1970s that a monkey could learn to raise the firing rate of a single motor cortex neuron when that neuron was wired to a reward. Operant conditioning of neural activity, it was called volitional control of neuronal firing. But the gap between one neuron and a working prosthetic limb remained vast. The first human brain-computer interface implant arrived in 1998, 4 years before the DARPA announcement. Philip Kennedy, with Emory University and his own company Neural Signals, implanted a neurotrophic electrode, a glass cone filled with growth factors, into a locked-in patient known in the literature only by initials. The patient produced distinct firing patterns for attempted speech, and Kennedy's team translated them into cursor movements on a screen. It was primitive, slow, and it worked. At Brown University, John Donahue had spent the 1990s working out how populations of motor neurons encode the direction, speed, and force of an intended reach. With engineers, he helped push a microelectrode array small enough to catch individual neurons yet robust enough to survive in living tissue. The result was the Utah array, a 10 by 10 grid of silicon electrodes, each a millimeter long, still the sensing element in clinical trials today. Donahue co-founded Cyberkinetics Neurotechnology Systems in 2001 to commercialize the array and drive it toward clinical trials. That company and the trial it launched would produce the most famous brain-computer interface publication in history. Hold on to the one thing every result so far has shared: a surgeon, an implant, a wire, a cooperating volunteer. Next, we look at what that trial actually achieved and, just as important, at what it did not. Cyberkinetics was founded in 2001 to carry that array into a clinic. Before we follow it there, we have to step back 1 year, to the demonstration that made the whole enterprise fundable. In 2000, in a laboratory at Duke University Medical Center, a monkey moved a robotic arm without moving its own. Read that experiment slowly. Almost everything that came after it rests on what happened in that room. Miguel Nicolis, then at Duke, had spent years perfecting a technique, implanting bundles of fine microwires into the motor cortex of owl monkeys and rhesus macaques, then recording from as many as 100 separate neurons at once while the animals performed trained reaching tasks. Every word there matters. Implanted, motor cortex, trained animals. This is demonstrated science, published and replicated, and it is nothing like listening from outside a skull. Consider what that recording actually demands. Each microwire has to sit within range of a firing neuron without tearing the tissue around it. The signals are measured in microvolts, millionths of a volt, and must be amplified and digitized while rejecting electrical noise from the building, the equipment, and the animal's own muscles. Contact at that scale is not a detail. It is the entire reason the method works at all. Then comes the harder half. 100 electrodes produce a flood of time-stamped firing events, and something has to turn that flood into a single continuous estimate of where the animal intends to reach next, updated faster than a real arm can move. That decoding problem, not the surgery, is what had blocked the field for 30 years. Nicolis's team solved it for one variable, under tightly controlled laboratory conditions. The task itself was ordinary. A macaque learned to move a cursor on a screen with a joystick, and to reach out and grasp a piece of food. Months of training preceded any decoding. Only once the algorithm had characterized how that particular animal's neurons encoded reach direction, a per-subject calibration valid for that one animal and no other, could the experiment proceed at last to its famous second half. Then the researchers changed the paradigm. They disconnected the joystick. The cursor, and later a robotic arm, were driven entirely by the decoded neural signal. The monkey kept producing the motor-cortical firing patterns for a reach, and the arm kept reaching, although its own biological arm was no longer coupled to anything. In some sessions, the animal's arm gradually stilled. The firing patterns alone were enough to move the machine. Now hold the finding at the right size. What the decoder read was a reach direction in 2 or 3 spatial dimensions, a continuous variable with a well-understood neural code, built on decades of work mapping the directional tuning of motor neurons. It was not reading a sentence. It was not reading an emotion. It was estimating where a hand was about to go, the one thing motor cortex evolved to encode. The deeper result was about the brain, not the robot. In those sessions, the animal appeared to fold the external actuator into its own motor control loop, treating the machine as something it could move directly. That matters enormously for prosthetics and rehabilitation, and it raises a real philosophical question about where a body ends. The work appeared in Nature in 2000. It says nothing whatever about reading a mind from across a street. Almost none of that reached the newspapers. What reached the newspapers was a monkey moving a robot arm with its mind. Strip out the implant, the shielded room, the months of calibration, the trained animal doing exactly what it was trained to do, and you are left with a headline that seems to license any claim at all. The omissions are where the confusion in this field is quietly manufactured. So let us be exact about the year 2000. None of it was remote. None of it was covert. None of it extracted content the subject had not intended to produce. It required a laboratory, a surgical implant, a technical team, a shielded recording room, and months of calibration on one animal. The reach was read by a wire instead of a tendon. That is the whole of the difference. The knowledge base entry on synthetic telepathy as a research term puts the distance plainly, and it is worth hearing in its own words. Direct contact sensors, extensive training, controlled environments. Those three conditions hold for every demonstrated brain-machine interface in the published literature, without exception. Keep them in mind because much of the literature we examine later in this episode quietly drops all three, one clause at a time. Alongside the demonstrated work sits a second register, things filed, proposed, and funded. The knowledge base records a RAND report on brain-computer interfaces for national security that listed synthetic telepathy among 7 potential capability sets, and an NBC News story from 2008 about an Army-funded program to decode imagined speech. Both are real documents. Neither is a working device. A proposal proves intent to try, nothing more. Set the milestones side by side and the pace of the field becomes visible. Jacques Vidal names the brain-computer interface in 1973. Philip Kennedy implants a locked-in patient in 1998. Duke's monkey moves the arm in 2000. DARPA funds the program in 2002. The first BrainGate participant is implanted in 2004. 31 years, then, from a coined phrase to one wired human. In 2004, cyberkinetics carried the Utah array out of the animal laboratory and into a hospital. The BrainGate trial enrolled its first participant that year, a young man with a spinal cord injury at the 4th cervical vertebra, paralyzed from the shoulders down. He could not use his arms or his hands. He volunteered for brain surgery in order to find out whether an implant could give him a cursor. The device implanted into the hand area of his primary motor cortex was the Utah array, a 10 by 10 grid of silicon microelectrodes, 96 of them recording, each about a millimeter long and tapered to a fine tip. The whole chip is roughly the size of a small aspirin tablet. It does not rest on the head. It is pushed into living cortical tissue, and it stays there for as long as it works. The surgery took place at Rhode Island Hospital, performed by a neurosurgical team led by Gerhard Fries. What came out of the skull afterwards is the detail people forget. A percutaneous connector, a plug mounted on the head, accessible through the skin, running by cable to an amplifier, a signal processor, and a computer. There was no wireless link. The signal traveled down a physical wire passing through his scalp. On the 13th of July, 2006, the journal Nature published Neuronal Ensemble Control of Prosthetic Devices by a Human with Tetraplegia, by Lee Hochberg, John Donahue and colleagues at Brown University, Massachusetts General Hospital and Harvard Medical School. One participant. The results were remarkable. He moved a cursor to a target, selected it, opened simulated email, changed television channels, drew on a screen, and closed a robotic hand. Hold the two columns apart. Demonstrated in 2006. An array inside the motor cortex, a cable through the scalp, a decoder trained over repeated sessions, a consenting participant, a hospital laboratory. Claimed, no implant, no contact, no calibration, no consent, at unspecified distance. That is not an extrapolation from the first column. It is a different proposition by orders of magnitude, and the gap is not itself evidence of a secret. The story does not end well, and the reason is instructive. After roughly a year, the signal degraded. Microglia, the brain's own immune cells, Treat a penetrating electrode as a foreign body and wrap it in glial scar, insulating the tips from the neurons they were placed to hear. The decoding fell away. Making an electrode the brain does not wall off remains one of the unsolved problems of the field today. Matthew Nagel died in 2007 of an infection unrelated to the implant. He was still in his 20s, and his name belongs beside the researchers in that record. BrainGate continued testing wireless versions, but wireless means a transmitter on an implant, not sensing at a distance. Implant, trained decoder, consenting subject. The architecture has not changed. What changes next is not the hardware. It is the language used to describe it. So the architecture has never changed. An implanted array, a wire through the scalp, a decoder trained on one person over weeks, a volunteer who agreed. Hold that picture because we now turn back to the document at the center of this episode, the so-called mind weapon paper, cataloged in the knowledge base as Item 19. Buried inside it, among its largest claims, is one unusually candid technical sentence. It deserves reading in full. Read that slowly. The effort will require nanotechnologies, future ones, in order to make the measurements at all, and in order to build the devices that would receive signals from a brain and push signals back into one. Both directions. Neither built. That is not a promise of capability. It is a description of missing hardware, written by the document's own author, sitting in the middle of a paper about mind weapons. Treat that sentence as a confession rather than a forecast. In its own words, the fine-grained hardware needed for two-way, brain-to-brain transfer has not been built. The measurements cannot yet be made. The receiver does not exist. The transmitter does not exist. And then, remarkably, the document carries straight on, describing what such a system would do to a person, as though the missing hardware had quietly been supplied somewhere between one paragraph and the next. The word nanotechnologies is doing precise work in that sentence. Reading a reach, a hand moving toward a target needs access to the few hundred neurons that the Utah array and Nicolelis's microwires can partly capture. Reading a thought, a feeling, or an act of will would need resolution finer by orders of magnitude, spread across many regions at once, and integrated in a way no recording technology in existence can approach. Put a number on it. The array implanted in the 2006 BrainGate trial carried 96 silicon electrodes on a square of silicon about 4 millimeters across, sunk into one patch of motor cortex. On a good day, it listened to perhaps 100 neurons. The human brain holds roughly 86 billion, by the 2009 cell count of Azevedo and colleagues. That is the recording bandwidth the whole demonstration rests on. The document asks for two things: receiving signals from a brain and transmitting signals back into it. The second is far weaker than the first. The only demonstrated way to write anything into a living human cortex is transcranial magnetic stimulation. A coil held against the scalp, firing a magnetic pulse that can twitch a finger or produce a flash of light called a phosphene. It is contact hardware, and it is crude. Here is the tool to carry forward. When you meet a claim about remote mind reading or brain-to-brain transmission, ask one question. Does it rest on a technology that exists or on one that, in the claimant's own words, still requires an enabling breakthrough? For its most ambitious claims, this document answers that question itself in advance, and the answer is no. Hold on to that sentence. It will settle several arguments in later chapters. It helps to keep three registers apart and never let them merge. Demonstrated means a named study, a named journal, a named year, subjects, and hardware you could photograph. Filed means a patent, a contract, a workshop report, proof that a document was written, not that a device was built. Claimed means testimony and inference about covert use on unwilling people. All three matter. Only the first is evidence of capability. Two documents in the knowledge base are worth naming here. One, cataloged in a bibliography assembled by the journalist Sharon Weinberger, is a National Science Foundation workshop report from 2002 on converging technologies, pairing nanotechnology with the brain-machine interface. The other is a RAND report that lists synthetic telepathy among 7 possible capability sets for national security. Both are documents about what might be built. Neither describes a working device. There is a move at this point that this genre makes almost automatically, and it should be resisted. If nothing has been published, the reasoning runs, then the working version must be classified. That does not follow. Absence of a published capability is not evidence of a hidden capability. It is simply absence. The honest position is narrower and harder. The gap remains a gap until someone shows the hardware, the subject, and the result. Now the pivot of the entire episode. A single sentence from the same document which deserves reading twice. Everything demonstrated so far has been one narrow thing. A person's own intention to move a limb, generated deliberately, read through a wire that person agreed to have fitted. The sentence that follows leaves that ground completely. Watch what it adds and watch just as carefully what it quietly declines to specify. Both matter. 3 claims are packed into that one line. First, that intellectual data, the content of a thought, the meaning of a message, not merely an instruction to move a hand, can travel from one person to a second without speech. Second, that emotional data can travel with it. Feelings, moods, the felt quality of an experience. Third, and most ambitious, that volitional information can travel too, the experience of deciding, of choosing one course over another. Understand why step 1 worked at all. The intention to move a limb has a known neural origin in the motor and premotor cortex. It has a known code, individual neurons are tuned to direction. It has a known timing. Firing rates shift before the limb does. And it has decades of replicated, peer-reviewed characterization across several species and many laboratories. In neuroscience, it is one of the best understood signals we have. Now notice what has quietly changed. The subject of the sentence is no longer one person controlling one machine. It is 2 separate human brains with content moving between them. And notice what is missing. No device is named. No distance is given. No mechanism is described. No subject, no measurement, no result, no citation. The sentence asserts a destination while saying nothing about the road, and every omission is where a testable claim would have started. Being precise here is not a way of dismissing anyone. The knowledge base is blunt on both halves of this. No verification has validated the existence of such capabilities, and the belief in them still shapes the daily lives of thousands of self-identified targeted individuals. Mental privacy and cognitive liberty are genuine questions in an era of fast-moving neural research. Getting the science right is what makes those questions arguable in public. So picture the claim as a staircase with 3 separate steps, because bundling them together is exactly how an unproven idea borrows credibility from a proven one. Step 1. Decode a deliberate movement intention from one cooperating, wired-up person. Step 2. Decode open-ended emotional and volitional content. Step 3. Write that content into a second brain so the second person experiences it as their own. 3 steps. 3 completely different evidential positions. Step 1 is Tier 1, demonstrated. It is limited, invasive, and it degrades as scar tissue closes around the electrodes, but it is real and it is repeated. Step 2 has no comparable public demonstration. Effective neuroscience cannot agree what the neural signature of a feeling looks like. Decision neuroscience is still arguing whether a decision has one localizable marker at all. That is not an engineering shortfall. It is unfinished basic science. Honesty demands one refinement here. There is published brain-to-brain work. In 2014, Karlsgrau and colleagues reported in the journal PLOS-1 that a volunteer in India, wearing an EEG cap, sent a pre-agreed binary code over the internet to volunteers in France, who wore stimulation coils and saw flashes of light. A second team, led by Rajesh Rao, did something similar the same year. Read the conditions carefully. What crossed between those two heads was not a thought. It was a string of ones and zeros that the two computers had agreed, in advance, would stand for a greeting. One volunteer wore electrodes. The other wore a coil against the scalp. Both consented. Both were calibrated. The internet did the traveling. Strip the hardware away and nothing crosses at all, which is precisely the distance between this experiment and the document's claim. So that is the tool this episode offers. Name the staircase and walk any claim up it, one riser at a time. Which step does the evidence actually support? Ask it, and you no longer have to accept or reject the whole idea in one move. Next, we go inside step 2 and look at why it is so hard at Benjamin Libet's readiness potential, and at what neuroscience still cannot say about a feeling. We left the staircase at step 2, and step 2 is where the climb stops. It is tempting to call that an engineering shortfall: better sensors, more electrodes, faster computers. It is not. To decode a decision, you must first know what a decision looks like in the brain. Neuroscience has been arguing about that for more than 40 years, in public, in print, and it has not settled the question. The claim on the table is that emotional and volitional information can be lifted out of one brain and delivered into another. The knowledge base is blunt about where the real technology stands. Brain-computer interfaces require implantation or sophisticated EEG monitoring over short distances. But set the hardware aside. Volition means willing, choosing, deciding. For the claim to mean anything, there must be a findable thing in the brain that is the decision. The story starts in 1965 with two German neuroscientists, Hans Helmut Kornhuber and Ludwig Dieck. Recording scalp electrical activity, they found a slow negative drift in the signal that began before a voluntary movement. They called it the Bereitschaftspotential, the readiness potential. It rose roughly 1 to 2 full seconds ahead of the act. The brain, on this measure, was getting ready to move well before anybody said they had chosen to. In the early 1980s, the American neuroscientist Benjamin Libet turned that finding into an experiment about consciousness. His design was elegant and cheap. A participant sits before a fast-moving clock. They flick a wrist whenever they like. They note where the hand was at the instant they felt the urge to move. All the while, EEG electrodes record the readiness potential. 2 clocks, then the brain's and the person's own report. Laid out in order, one trial runs like this. The readiness potential begins its slow climb. Some hundreds of milliseconds later comes the moment the person will afterwards name as the decision. Then the muscle fires. Then, after the fact, the clock reading is reported. Everything hinges on that third element, a subjective judgment about when something happened, recalled from memory a second or two after the event itself, and never independently checked. Libet published the result in the journal Brain in 1983, and it landed hard. The readiness potential began to rise, on average, 350 to 550 milliseconds before the moment participants said they had consciously decided. Roughly half a second. The motor preparation was underway before the conscious mind reported making a choice. For decades on, that half second is still being fought over. The implications were immediate and incendiary. If the motor machinery starts preparing an act before the conscious self knows about it, what is the conscious self doing? Is the feeling of deciding a story stitched together afterwards, once the cortex has already committed? Libet himself did not think free will was dead. He argued a person could still veto the act in flight. Almost nobody on either side found that answer satisfying. The critics arrived quickly, and they have grown more sophisticated. The philosopher Daniel Dennett argued that the design confuses two different things: an objective neural precursor and a subjective timing judgment that is itself constructed, not read off a clock. On his account, the famous gap is an artifact of how the measurement was taken, not a window onto unconscious determinism. That is a methodological objection, and it has never been fully answered. A second line came from inside the paradigm. The neuroscientist Patrick Haggard refined Libet's method and found that the sense of agency, the feeling of having authored your own action, does appear to be assembled after the event. But Haggard drew a different moral. That construction, he argued, does real work. It is how we learn from our actions and how we hold ourselves responsible for them. Useful, not illusory. Then, in 2012, Aaron Scherger and colleagues published a rereading in the Proceedings of the National Academy of Sciences. Their proposal, the readiness potential, is not a decision signal at all. It is spontaneous neural noise drifting until it crosses a threshold. Averaged across many trials, that random drift produces a smooth rising curve that looks like preparation but is largely an artifact of the averaging itself. Set the philosophy aside for a moment and look at the instrument. The knowledge base entry on synthetic telepathy puts the engineering problem plainly, and it is worth hearing in its own words. Scalp EEG is a blur. It sums the activity of millions of cells through skull and skin. Even where a signal exists, isolating one specific mental event from all that background noise is the whole of the difficulty. So here is where the volition half stands. Neuroscientists do not agree on what the neural signature of a single act of will looks like, or whether one exists at all. The knowledge base entry on artificial telepathy notes that such claims stray from scientific definitions and lack peer-reviewed validation. A filing describing decodable volitional information is naming a signal the field cannot define. Premature, not disproven, and not the same thing. Volition is one half of the claim. The other half is emotion, the assertion that a feeling can be lifted from one person and installed in another. If anything, emotion is the harder case. It sounds easier, because emotions feel obvious and nameable from the inside. But the science of how a feeling is built in the brain has moved a long way from the model most of us were taught. For most of the 20th century, the dominant model was the basic emotions view, associated above all with Paul Ekman's work in the 1960s and 70s. A small set of emotions universal across cultures, each with its own hardwired circuit, its own pattern of bodily arousal, and its own recognizable face. Under that model, decoding a feeling is a measurement problem. Find the circuit, read the signal. Hard, but conceptually simple. The classic list is short. Happiness, sadness, fear, anger, disgust, surprise. 6 categories held to be universal, each supposedly with a home in the brain. Fear to the amygdala, disgust to the insula, and so on. That neatness is exactly what made the model attractive, and exactly what modern effective neuroscience has spent 30 years dismantling. The categories survive as words we use. The circuits behind them have not survived. In 2019, a comprehensive meta-analysis in Psychological Bulletin by Kristen Lindquist, Tor Wager and colleagues went through decades of emotion neuroimaging. The finding was blunt. No single brain region, and no single network, activates consistently and specifically for any one emotion category. Not for fear, not for anger, not for any of them. Whatever a feeling is, it is not one single place lighting up on cue. Take the best-known example. Fear does not reliably and exclusively activate the amygdala. The amygdala is busy during other emotional states, and during tasks with no emotional content at all. Meanwhile, fear itself shows up across dozens of distributed regions, and the particular combination shifts between people, between contexts, and between 2 episodes of fear in the very same person. The textbook mapping simply does not hold, and it has not for years. The most influential replacement comes from Lisa Feldman Barrett, whose theory of constructed emotion argues the brain has no dedicated emotion circuits at all. A feeling is assembled in the moment out of more basic ingredients. Interoception, the brain's read on the body's internal state. Sensory input from outside, learned concepts like anger or fear, and constant prediction against context. The emotion is the categorized experience of that whole assembly. Barrett's model is supported by imaging meta-analyses, by cross-cultural work on expression, and by the field's long failure to find one-to-one mappings. The knowledge base makes the same point from the engineering side. Decoding algorithms need extensive training for each individual user, because neural patterns vary so much between people. Barrett explains why. If the pattern is a personal construction, it was never going to generalize to anyone else, or to any other moment. None of this makes the questions unimportant. Emotion and volition are live, actively researched science. It means the claim outruns the evidence. The knowledge base states it plainly. Despite decades of research, no verified, functional artificial telepathy system has been demonstrated, and the gap between laboratory work and remote, continuous decoding remains vast. Every working interface still needs contact hardware, calibration, and a willing subject. Keep that gap in view. That leaves the real machinery exposed. Why does the distinction between a motor decoding interface and a thought-transmitting one matter so urgently? Because sloppiness about it is how an unproven claim borrows credibility from a proven one. You hear that the Defense Advanced Research Projects Agency funds brain-machine interfaces, which is true. Then, in the same breath, you hear that thoughts are being transmitted between people. Your respect for the first proposition is quietly moved onto the second. The move does not need to be stated as an argument to work as one. It runs in 4 beats, and once you have seen them, you will see them everywhere in this literature. A real program is named. A real scientist is quoted. A real grant is cited. And then, somewhere between the citation and the conclusion, the claim quietly grows properties that the cited source never mentioned. Mere adjacency does the persuading. Which properties? Watch carefully what gets added on the way from the footnote to the headline. Distance, covertness, the absence of consent, emotion, volition, continuous operation, day after day, a specific person singled out, and no calibration, no training session, no cooperation of any kind. Not one of those appears in the grant abstracts, the journal papers, or the patent filings. They arrive later in the retelling, and they arrive entirely unannounced. Set the 2 columns beside each other and the transfer becomes visible. What the citation actually supports is funded, published, unclassified research using contact hardware on volunteers cooperating with a task. What the claim asserts is remote reading of a mind that never agreed, at a distance, without hardware, without warning. The second is not a longer version of the first. It is a different proposition wearing the first one's clothes. And the genuinely impressive results all sit in the first column. Our knowledge base holds the citation for a wireless brain-machine interface for real-time speech synthesis by Frank Gunter and colleagues, driven by an electrode implanted in the speech cortex of a locked-in patient. It holds the rat-to-rat brain-to-brain experiment too, where both animals carried implanted arrays and the signal passed between them through a computer link. Real work. Contact hardware every time. The knowledge base states the boundary in one sentence. Current synthetic telepathy systems, it says, require direct contact sensors, meaning EEG caps and muscle electrodes, plus extensive user training and controlled environments, and they achieve only limited vocabulary recognition. Then comes the line that matters most for this episode. No peer-reviewed research has demonstrated remote, non-consensual, or real-time decoding of complex, private thoughts at a distance. That is the published record, stated plainly. It would be easy and wrong to call this dishonesty. Often it is enthusiasm, the pull of dots that genuinely seem to connect. Often it is something more sympathetic still, a community's need to make sense of an experience that feels technological when no sufficient, publicly acknowledged technology exists. Our knowledge base records the consequence. Belief in synthetic telepathy shapes the lived experience of thousands of self-identified targeted individuals, whatever its verification status. But intention does not change the arithmetic. A merged claim is weaker than a calibrated one, because anyone who checks a single citation can take it apart. So let us check one. The most concrete, most checkable real-world sequel to all of this arrived in 2008, carrying a name that did more damage than any critic could have managed. A $4 million Army grant for something called synthetic telepathy. The program had a real lead investigator. Michael Dzmura was, at the time of the award, a professor and the chair of the Department of Cognitive Sciences at the University of California, Irvine, one of the oldest and most prominent cognitive science departments in the United States. His research career already spanned more than 2 decades. The distance between the man and the headline is, in miniature, the distance this entire episode is about. $4 million, awarded by the United States Army Research Office in August 2008. The formal title was Synthetic Telepathy, a brain-computer interface for communication. That is a funding record, a contract, a line in a budget. It proves that the Army paid for basic research into decoding brain signals. It does not prove a device, a deployment, or a capability. A grant is a question being asked, not an answer delivered. So what did he actually study? Visual perception, attention, and computational neuroscience. The mathematical modeling of how the brain separates figure from ground, how attention sharpens some neural responses and dims others, how color and motion are bound into one coherent percept. Quantitative, model-driven work in the tradition of visual psychophysics. He was not a weapons developer. He was not a mind control researcher. He was a scientist who studied seeing. Put the dates in a row. 6 years earlier, Robert Asher's memo had circulated. 2 years earlier, Matthew Nagel's cursor had appeared in Nature, driven by an array implanted in his motor cortex. In August 2008, the Army grant was awarded. In October, NBC News ran the headline, Army Developing Synthetic Telepathy. And today, more than 15 years on, no fielded Imagine Speech decoder exists anywhere in the open record. The award was an ordinary multidisciplinary university research initiative grant, MURI, the Pentagon's primary mechanism for funding basic, unclassified, university-based research across several institutions at once. The consortium Dzmura led drew in researchers from the University of Maryland and Carnegie Mellon University, combining EEG signal acquisition, speech neurophysiology, machine learning, and human-computer interaction. Unclassified matters here. This was work intended to be published, criticized, and replicated in the open literature. The public materials, a UC Irvine press release in August 2008, and coverage by NBC News and the Associated Press, describe 2 parallel threads. First, Imagine Speech. Can the electrical signature of a silently rehearsed word be told apart from other brain activity and classified from a limited vocabulary? Second, Direction Intention. Can the signature of a choice, left rather than right, be decoded well enough to drive a menu? Both threads shared one design boundary, and it is the boundary that matters most for this series. The system was specified as non-invasive. Scalp electrodes applied on the outside of the head, rather than surgically implanted ones. That single word carried enormous consequences. A scalp electrode has no access to individual neurons. It records the summed, smeared electrical activity of millions of them, filtered through skull, fluid, membrane, and skin. Compare the 2 kinds of hardware honestly. Nagel's implant was an array of 96 microelectrodes sitting in cortex, close enough to resolve the firing of individual cells, and it took neurosurgery to place. The Irvine system used electrodes resting on skin, averaging millions of neurons at once. Both are contact devices. Neither works at a distance. Between them lies a gulf in signal quality that no amount of clever software closes. How much is lost on the way out? By the time the signal reaches the scalp, it has been attenuated by roughly a factor of 10 to 100 compared with what an implanted electrode receives. What survives is rich in time. The electroencephalogram resolves events down to milliseconds. It is poor in space. It cannot tell you with precision where in the brain a signal began. Timing, yes. Address, no. The second boundary was volition. The system had a signal to decode only when the wearer actively, deliberately generated the brain state tied to a specific word or a specific choice. It could not extract content from a passive mind, and it was never designed to. It could not function on anyone who was not wearing the cap and cooperating with the task. Consent here was not an ethical add-on. It was an engineering precondition. Picture the users the army actually had in mind. A soldier who needs to compose a short, silent message in an environment too loud and too dangerous for speech. A stroke patient who can no longer produce words but can still think them. That is a genuinely valuable research goal with direct clinical applications. It is also a categorically different thing from reading an unwilling stranger's mind, unannounced from somewhere else. And notice how little of that survives inside the phrase synthetic telepathy. The program's own name preserved none of the distinctions for anyone who encountered only the headline. So before we go further, it is worth looking hard at the apparatus itself, the cap, the gel, the wires, and the microvolts, because the hardware settles more arguments than any amount of rhetoric ever will. That is exactly where we turn next in close detail. So picture the actual apparatus behind the headline. An EEG cap is a fabric or silicone skull cap, sized to fit snugly against the scalp, studded with small metal electrodes, 32 of them, or 64, or 128, or 256, depending on the application. Each electrode needs a dab of conductive gel or saline paste to push a connection through hair, skin oils, and the dead outer layer of the epidermis. What does one of those electrodes actually pick up? Not a thought. It registers the combined electrical field produced by millions of cortical neurons firing together, specifically the postsynaptic potentials of pyramidal cells, which, when large populations synchronize, produce a voltage fluctuation detectable at the scalp surface. That is a population average, smeared through skull and skin. It is the sound of a stadium crowd, not the words of any single person in it. And the signal is tiny. Scalp EEG is measured in microvolts, millionths of a single volt. That is the whole recording, the entire quantity of information the cap collects. Everything the decoding software will ever have to work with arrives at that amplitude, and it arrives buried. The engineering problem of imagined speech decoding begins here, not with secrecy or classification, but with a whisper-level voltage read through bone, skin, and hair. Now consider what competes with it. A single eye movement generates the electrooculogram, orders of magnitude larger than the brain signal underneath. Clenching your jaw produces an electromyogram just as massive. The mains wiring in the wall hums at 50 or 60 hertz straight into the electrodes. The amplifier adds its own thermal noise. Before any decoding begins, the researcher spends most of the effort separating the signal from that surrounding din. Out of that noisy trace, researchers hope to extract imagined speech, a specific semantic, content-laden mental act. As of this writing, that remains a genuinely hard and still developing research problem. The EEG correlates of silently rehearsed words are weak, they vary from person to person, and they are difficult to separate from the correlates of attention, arousal, or the sheer subjective effort of doing the task at all. The brain does not label its own activity. So what has actually been demonstrated? Laboratory studies, including those published by Michael Dzmur's group at the University of California, Irvine, and by parallel efforts elsewhere, have reported classification accuracy better than chance for small vocabularies, 5 to 10 words, under carefully controlled conditions. That is a real, published result. It is also a narrow one, and the accuracy falls away sharply as the vocabulary grows, the room gets noisier, or the participant tires. Hold those two columns apart, because the whole episode turns on the distance between them. Every demonstrated brain-machine interface needs invasive or contact hardware, an implanted array, or electrodes pressed to the scalp with gel. It needs long per-subject calibration and someone who is cooperating. Remote, contactless, covert, uncalibrated operation on an unwilling person is not a nearby extrapolation from that. It is a different claim by orders of magnitude. Here is the plainest test of that gap. Our knowledge base notes that a RAND report on brain-computer interfaces for national security listed synthetic telepathy as one of 7 potential capability sets. Potential being the operative word. More than 15 years on, no commercial, field-deployable Imagine speech decoder exists. Not a covert one, not an overt one. No product a hospital can buy, no unit a soldier can carry. The overt version would have to exist first. The TI-1 voice knowledge base reaches the same conclusion in its own entry on the subject, and it is worth quoting because it comes from inside our own archive rather than from a skeptical outsider. The same archive notes that no documented, independently verified case of synthetic telepathy as the community describes it exists in the public record. That is our own finding. We report it because honesty about the record is the whole point. That is the documented shape of synthetic telepathy as real science actually built it. A cap, a laboratory, a willing participant, and a noisy signal that can tell a handful of imagined words apart better than chance. By the standards of neuroscience, that is a genuine achievement. It is also the visible opposite of reading an unwitting stranger's mind at a distance. Now to the program that paid for it and what became of it. For $1 million. That is the reported size of the 2008 Army Research Office grant, publicly announced, covered by the University of California, Irvine's own press office and by national outlets at the time. Eric Bland's report for NBC News, dated the 13th of October 2008, carried the headline, Army Developing Synthetic Telepathy. Nothing about that announcement was hidden. It was a press release. It is worth pausing on what a MURI actually is. Multidisciplinary University Research Initiative, a standard Pentagon mechanism for funding basic, unclassified university research. Not a black budget. Not a special access program. Not compartmented weapons development. The work it pays for gets published in peer-reviewed journals, presented at open academic conferences, reviewed by independent scientists, and built on by later academic work. That is the entire purpose of the instrument. And weigh the money honestly. MURI grants typically run 3 to 5 years, span several universities, and are explicitly meant to produce foundational knowledge and train graduate students, not finished operational hardware. For $1 million spread across 3 universities over 5 years is roughly the cost of a single component of an advanced fighter jet engine. By Pentagon standards, that is not the signature of a crash weapons program. It is the signature of a seminar. Lay the public record out in order. 2008. The grant is awarded and announced. The same autumn, NBC News and Wired's Noah Shachtman both cover it. 2009. DARPA opens Silent Talk, described in our knowledge base as a basic research initiative exploring the feasibility of EEG-based communication. It runs to 2012. And then, in the open record, nothing operational follows. The papers keep coming. The hardware does not. Meanwhile, the science flourished. Since 2008, Imagine speech decoding has spread from EEG to related non-invasive signals, magnetoencephalography, or MEG, which measures the magnetic fields produced by neural currents, and functional near-infrared spectroscopy, or FNIRS, which tracks blood oxygenation. Hundreds of peer-reviewed papers report incremental gains in accuracy and vocabulary size. These are real results, and every one of them still needs the head placed inside a shielded scanner or a sensor pressed against the scalp. Now the crucial discipline. No public record, not the peer-reviewed literature, not the defense press, not the patent files, not the procurement databases that track Pentagon acquisition, shows the 2008 program becoming a fielded operational system. But be careful what you do with that. An absence of published capability is not evidence of a concealed capability. That inference is this genre's characteristic failure, and we are not going to make it here. Named alongside the MURI material in the source document is a contributor of an entirely different kind, and precision here matters. Richard Allen Miller is credited in the Mind Weapon document, and across the wider TI literature, with developing the concept of a brain transmitter, a device said to send structured information directly into a human brain without the recipient's awareness or consent. That is a claim. It has never been demonstrated. Miller's background is eclectic. Public biographical material describes work as a researcher in alternative agriculture, an author of books on herbal medicine, and a self-described futurist and counterculture writer. He has claimed expertise in physics, but no record of formal advanced training, or of a peer-reviewed publication in a mainstream neuroscience or engineering journal has been located. Our knowledge base dates his early Mind Wars paper to a conference in Sisters, Oregon, in July 2001. None of this is disqualifying. Independent researchers have made genuine contributions throughout the history of science, and lacking an institutional affiliation does not make a claim false. But it does place the claim on a different and weaker tier, one where nobody else has checked the data, described the method, or tried to replicate it. That is the sorting operation any honest investigation has to perform, and it is not an attack on anyone's character. And the failure to perform it is exactly the error this episode exists to expose, presenting a self-published brain transmitter theory in the same confident register as the 2006 Nature paper on the brain gate implant. Two very different things, spoken with one voice. Keep the tiers separate and the picture clarifies. Next, we turn to what the demonstrated hardware could and could not do if someone tried to point it at an unwilling person. Miller's theory does not float free. It rests on real, findable patent filings, documents you can pull from the United States Patent and Trademark Office by number. Some were filed in the 1970s and 80s. Others were granted in the 1990s. They describe silent communication systems, methods for generating signals that a person perceives without ordinary hearing. Their existence is not in dispute. What that existence proves is an entirely different question. In the technical language of patent claims, these filings specify carrier frequencies, modulation schemes, pulse patterns, and transducers, hardware meant to deliver a signal the recipient hears without it being audible. That is the microwave auditory effect, which Part 13 examined, and which has a narrow but genuine scientific literature behind it. The knowledge base names the two most cited examples, one of them titled Apparatus and Method for Remotely Monitoring and Altering Brain Waves. Here is the sentence to hold on to. The leap from a patent exists to the device works at range on an unconsenting person as a weapon is a leap that any serious evidentiary standard must refuse to make without additional evidence. And as far as we could locate, that additional evidence is absent. Not suppressed, not hidden. Simply not present in the record that anyone can check. Say the gap out loud. So what does a patent examiner actually certify? 3 things. That the idea is novel, different from what has already been patented or published. That it is non-obvious, not a trivial tweak any skilled engineer would think of. And that the application describes the invention well enough that a person of ordinary skill could, in principle, attempt to build it. In principle, on paper, against the existing record of prior art. And here is what the examiner never does. The examiner does not build a prototype. The examiner does not test whether the device works at range, on human subjects, covertly without consent. No laboratory bench is involved anywhere in the process. A granted patent is a statement about prior art and paperwork, not a laboratory result, not a clinical trial, and not a fielded capability. Those are 4 different things, and they are not interchangeable. Patent offices around the world have granted filings for devices whose physics is to put it gently, unsupported. Perpetual motion machines, anti-gravity generators, telepathic communication systems, endless variations on energy healing and consciousness-based technology. A grant means an idea met formal criteria at one moment, judged by one examiner inside one patent system. It does not mean the thing has been built, tested, miniaturized, weaponized, and turned against people who never agreed to any of it. The knowledge base records how deep this habit runs. Judy Wall published a review of synthetic telepathy patents in MindNet Journal, Volume 1, Number 59. A later Intel filing on brain-controlled computing lists applications ranging from user authentication to telepathic communication. Both are real documents. Neither is a working machine. Cite the patent by number if you want to be precise, and then say plainly what a filing is and what it is not. Now hold that patent discipline alongside the source document's own most honest sentence. Buried inside the Mind Weapon paper, Knowledge Base 19, the same document that carries Miller's brain transmitter claim states elsewhere that the enabling technology for its wider vision does not yet exist. It says the two-way interface it imagines will require nanotechnologies that have not been built. The document asks us to believe in a capability whose hardware it admits is still missing. Both facts are true at once, and the discipline is to hold them without collapsing either. A real author, real patents, a real, serious question about neural privacy and where brain interfacing technology is heading. And, in the source's own words, an enabling hardware platform it admits is still unbuilt. Resolve that tension too quickly in either direction and you get either credulity or contempt. Neither is an investigation. The tension is the honest position. So state the honest position exactly. A working, covert, at-range brain transmitter has not been demonstrated in the public, peer-reviewed scientific record, nor in the open defense technical literature. That is a statement about the record, not a verdict about anyone's experience. The underlying questions are real and urgent. Where this technology is heading, what protections should exist before the capability arrives, where the ethical boundaries of neural interfacing should be drawn. Those questions deserve sustained attention. The knowledge base puts it carefully. Synthetic telepathy claims are not supported by scientific evidence, and yet the neurorights framework addresses legitimate concerns about the misuse of emerging neurotechnology. Both halves of that sentence matter. Policymakers and human rights bodies have taken up neural privacy precisely because researchers inside the field expect the capability to outpace the law. But arguing that we should prepare for an arrival and asserting that it has already arrived are different activities. So here is the rule this series applies, and it is worth repeating until it is automatic. Name real people and real filings precisely, as we have done with Miller and with the patent numbers. Never assert a contested mechanism as proven, and never, under any circumstance, name a living private individual as the covert operator of an unproven technology. That discipline is not dismissal. It is what keeps the subject inside serious conversation. Which brings us to the method this whole episode has been building toward. It is a sorting tool, and you can carry it into any document, any claim, any argument about brain-machine interfaces, and use it before you decide what to think. 3 tiers. Demonstrated, funded, open and developing, asserted. Every claim in this field belongs in exactly one of them, and most of the confusion comes from claims that quietly change tiers mid-sentence. Tier 1 is demonstrated, published in peer-reviewed journals, replicated across independent laboratories, shown to work over years by multiple groups. Tier 2 is funded, open and developing, real money, named investigators, published methods, results still partial and variable by the field's own standards. Tier 3 is asserted, claims for which no public, peer-reviewed, or credibly documented demonstration currently exists. Same subject, 3 completely different evidentiary weights. Keep them physically separate in your notes. Tier 1 has real occupants. The prosthetic arm and cursor control work from the BrainGate trial belongs here, a hair-sized silicon array implanted in the motor cortex of a paralyzed volunteer. Decades of animal research belong here too. So does the P300 speller, which lets a locked-in patient spell words by attending to a flickering letter on a screen. Every one of these is a genuine achievement. Every one required hardware touching the head. The lineage is checkable, name by name. Eberhard Fetz showed in the 1970s that a monkey could learn to control the firing of a single neuron. Emmanuel Donchin and Lawrence Farwell built the P300 speller in the 1980s, refined since across dozens of studies. Miguel Nicolis ran the primate experiments of the late 1990s and early 2000s. Then human clinical trials with implanted electrode arrays. Published, replicated, cited. Notice what every Tier 1 result has in common, because this is the load-bearing part. The subject is an active, willing, cooperating participant. The signal is their own consciously generated neural activity. The readout is approximate, imperfect, and confined to a narrow, pre-characterized neural code, trained on that individual over hours or days. Take away the cooperation, the contact hardware, or the calibration, and you do not have a weaker version of Tier 1. You have no result. Tier 2 is the frontier, and it is honest work. The 2008 Imagine Speech program belongs here. So does the wider field of EEG speech decoding, and its cousins using magnetoencephalography and functional near-infrared spectroscopy. So does the search for chronic implantable electrodes. The brain does not eventually wall off in scar tissue. The very nanotechnology the source document itself admits is still required. Real money, real investigators, unfinished results. Tier 3 is where the assertions live, and naming them precisely is not an insult. It is a filing decision. That intellectual data, emotional content, and volitional information pass between two people without speech, with no specified device, distance, or mechanism. That a remote brain transmitter has been built and aimed at unwitting targets. That covertness, distance, and non-consent have been combined in one working system, anywhere by anyone. No public demonstration currently supports these. And here is the discipline that makes the whole method work. Tiers 1 and 2 lend no automatic credibility to Tier 3. DARPA really does fund brain-machine interfaces, true, and not evidence that a remote mind transmission device exists. The Army did fund a synthetic telepathy program, true, and not evidence of a weapon that reads a stranger's thoughts across a city. Watch for that borrowing. Next, we state plainly what the public record does not show. That borrowing is the move to watch for. So now we do the opposite and state the negative plainly, because precision here is what separates a credible investigation from a credulous one. And because the fear that drives someone to ask about these technologies in the first place deserves an honest, evidence-anchored answer rather than a comforting one. Here, then, is what the published scientific and defense technical record does not contain. As of this writing, there is no published, peer-reviewed, or credibly documented demonstration of any device that reads structured thought from a non-consenting person's brain, or writes structured content into it, covertly, from a distance. Read that sentence slowly. Every qualifier in it is doing work. Take away any one of them and you are describing something else entirely. Something that in several cases has genuinely been achieved in a laboratory on a volunteer. Every genuine first-tier demonstration in the public record, the prosthetic arm work, the cursor control, the imagined speech decoding, decades of animal brain-computer interface research, shares three unglamorous requirements. A surgical implant or a worn scalp cap. Close physical proximity to bulky recording equipment. And, in every single case without exception, the active, informed, ongoing cooperation of the person whose brain was being read. Those requirements are not incidental. They are the experiment itself. Set the two side by side and the distance shows. Demonstrated systems need metal in or on the head. A subject sitting meters from an amplifier, weeks of per-person calibration, and a volunteer who signed a consent form. The asserted capability needs none of that. It works at range through walls on someone who never agreed and never trained. That is not a nearby extrapolation. It is a different claim by orders of magnitude. Look at the hardware that made the headlines possible. The array used in the BrainGate trial is a silicon square about the size of a baby aspirin, carrying roughly 100 microelectrodes, pressed into the motor cortex during open neurosurgery. The results, published in Nature in 2006, were real and remarkable. They were also produced by a wire running out of a paralyzed volunteer's skull to a computer in the same room. That is the price of admission to Tier 1, and it is worth saying out loud. A craniotomy, a pedestal bolted to the skull, infection risk, scar tissue, and an electrode array that the immune system slowly walls off. Research teams accept all of it because the participants volunteered, understood the risks, and wanted the cursor to move. Nothing about that procedure can be performed on a person who does not know it is happening. Name the 3 properties precisely, because vagueness is where this argument usually dies. Distance. Operation with no contact at all. Covertness. The subject never knows. Non-consent. The subject never agreed and never trained. Individually, each is discussed in the literature. Together, in one working system, they appear nowhere in the open scientific or defense technical record. That specific combination is the whole of the Tier 3 claim, and it is the part with nothing published behind it. And none of this is a claim that the field is standing still. Trace the line this episode has followed. The first human brain-computer interface implant in 1998, the DARPA program announced in 2002, the BrainGate results in 2006, the Army's $4 million Imagine Speech grant in 2008, and an accelerating, well-funded, global research effort ever since. The technology is moving fast. That is exactly why the sorting matters. The non-invasive side has the same shape. An EEG cap holds 24 wet electrodes against the scalp, held still in a quiet room. Before it decodes anything, the system must be trained on that one person's signals, often for hours, and retrained when the cap comes off and goes back on. A jaw clench or a blink can swamp the recording. This is delicate laboratory work, not surveillance at range. Now hear the other half of the sentence because it matters just as much. Saying that the record does not show this is not a verdict that the underlying fear is baseless. It is a statement about evidence, not about people. The questions driving that fear, who may record a brain, under what authority, with what remedy, are serious questions, and they are being asked by serious people inside the field itself. The knowledge base entry on synthetic telepathy puts the present state carefully. Practical systems, it says, remain confined to laboratory settings with small vocabularies and controlled conditions. Small vocabularies. Controlled conditions. Those 2 phrases carry the weight. Researchers themselves flag the trajectory. That is why a neurorights movement exists at all, and we come to it shortly. But caution about what might arrive is not a demonstration that it already has. So the honest number, as of this writing, is 0. Not 0 brain-computer interfaces, there are hundreds in dozens of laboratories on several continents. 0 demonstrated systems that combine all 3 properties at once. And here is the trap this genre falls into every time. Absence of published capability is not evidence of a hidden one. A gap in the record is a gap. It is not a secret program. One last piece of vocabulary hygiene before we close this thread, because the central confusion of this episode is, at root, a labeling problem. 2 words, synthetic telepathy, carry 2 completely different meanings across the literature we have examined. Failing to distinguish them is precisely how the confusion propagates, from a press release to a forum post, to a person's understanding of what is happening to them. 2 meanings, 1 phrase, no warning label between them. The first meaning is narrow, academic, Tier 2, the one attached to the 2008 Army MURI grant. EG-based, non-invasive, consensual, aimed at letting a willing wearer compose a short message or pick a menu item by thinking it. The second meaning is broad and popular. Covert, remote, non-consensual thought reading or thought insertion by unknown operators against unwitting targets. Both meanings use the identical two words. The referents are not remotely the same. Now watch how the two meanings touch. The press coverage of the Army grant ran under headlines using the phrase itself. Army to spend $4 million to study synthetic telepathy is one. Cataloged in a bibliography held on TI1 Voices knowledge base at one.witisk.org. Nothing in that headline is false. But it hands the popular meaning a set of borrowed credentials it never earned. So be precise about what $4 million actually bought. A basic research program, run at universities, published in the open literature, in which a cooperating volunteer wearing a scalp cap tried to compose a short message by imagining the words. No implant, no range, no unwitting subject, and no credible path then or since from that program to a remote, covert, non-consensual device, a claim the investigators themselves never made. Follow one listener's path because it is entirely reasonable and it still ends in error. They read the headline, "The Army is funding synthetic telepathy." Months later they read the phrase again, in a discussion of remote mind reading. Same two words, so surely the same capability, and now the Army appears to have proved it. That inference is wrong. But the language did almost all of the work and nobody lied. The knowledge base entry on the research term states it about as plainly as it can be stated. The gap between laboratory capabilities, direct contact sensors, extensive training, controlled environments, and the remote, continuous decoding described in targeted individual accounts, it says, remains vast. Vast is the operative word. And the conceptual overlap between the two meanings is exactly what keeps the phrase circulating on both sides of that gap, unlabeled. So here is the small discipline, and it costs nothing. Call the Army program what it was, non-invasive imagined speech decoding. Reserve the phrase synthetic telepathy for what it has become, a warning label, a signal that a claim has arrived unsorted and needs placing on the ladder before anyone acts on it. That forces the speaker to say which meaning they mean. It stops the listener borrowing credibility from the wrong one. Carry that habit forward because the next part of this episode needs it. We turn now to the people who have been asking these questions from inside the science itself, the neuroethicists, the human rights lawyers, and the legislators behind the neurorights movement. Their concern about mental privacy is real, urgent, and argued entirely within the demonstrated and funded tiers. That is what disciplined alarm looks like, and it is worth studying closely. That vocabulary problem has a home outside this series. While the phrase synthetic telepathy drifted between two meanings, an entire academic field was being built around the harder question underneath it. Neuroethics was formally established as a distinct discipline in the early 2000s, with its own conferences, its own textbooks, and dedicated sections in the journals. It asks what neuroscience and neurotechnology may do to whom and under whose consent. Those are our questions too. The field's agenda is broader than any single device. It examines cognitive enhancement and where the limits of improving a healthy brain should sit. It examines neural privacy and whether information taken from a brain deserves a legal category of its own. It examines brain-based discrimination by employers, insurers, and courts. And it examines who should license and police a brain interfacing product before it ever reaches a patient, a soldier, or a consumer. Notice where the concern came from. The discipline did not arise in response to anything the targeted individual community said. It arose because neuroscientists, philosophers, and legal scholars, watching the very technology this episode has traced, concluded that existing law was inadequate for what was coming. The people closest to the hardware raised the alarm first. That is worth stating plainly because the assumption usually runs the other way around. The knowledge base entry on mental privacy compresses the whole idea into one sentence, and it is worth hearing exactly as written. Mental privacy is a proposed neural right that safeguards an individual's control over access to their neural data and the contents of their own mind. Proposed. Not yet a settled right in most of the world. That single word is doing careful work, and we should keep it there. The proposal that shaped the field arrived in 2017. Marcelo Ienca, a bioethicist at the Swiss Federal Institute of Technology in Lausanne, and Roberto Indorno, a human rights scholar at the University of Zurich, published a paper in the journal Life Sciences, Society and Policy. They argued that 4 new rights were needed. Note the register carefully. This is a peer-reviewed proposal for law, not a charge that a device exists. Their 4 proposed neurorights are worth learning by name. The right to mental privacy, control over who may reach your neural data. The right to mental integrity, freedom from unauthorized interference with your neural activity. The right to psychological continuity, protection of that unbroken sense of remaining yourself. And the right to cognitive liberty, freedom to think, and to refuse a device that touches your thinking. For rights, none of them yet universal. In 2023, Nita Farahany, a professor of law and philosophy at Duke University, published The Battle for Your Brain. Her argument is that existing protections for bodily autonomy were never written for an era in which corporations and governments can record and decode brain activity. She proposes regulatory frameworks comparable to those already governing genetic privacy. And note again what she does not claim. She does not allege a deployed covert weapon. That is the claim sitting at the center of the whole movement. Brain data, the argument runs, is not simply another row in a database beside your purchases and your location history. It is a domain of unique intimacy because it can carry the content of thought itself, and because you cannot meaningfully consent to a disclosure you never knew you were making. Whether the law agrees is still being decided country by country. One country has already acted. In 2021, the Chilean Senate unanimously approved a constitutional reform adding protections for mental privacy and cognitive liberty. Chile became the first nation in the world to place neurorights in its constitution. The reform declared that brain data should carry the same legal protection as organ tissue, that taking information out of a brain is closer to removing a piece of the body than to reading a file. Hold on to that comparison because it carries the reform's entire argument in one image. Organ tissue cannot be taken, traded, or examined without explicit consent. Chile's legislators decided that neural information belongs in exactly that category. It remains, as of this writing, the most advanced legal expression of the neurorights framework anywhere in the world, and it passed unanimously, which tells you the argument was not experienced as fringe by the people voting. The reform was championed by the neuroscientist Rafael Yuste at Columbia University, working with a coalition of Chilean legislators and legal scholars. Yuste is no outsider to this technology. His own laboratory work involves recording from and manipulating neural activity, and it was precisely that work which convinced him protection was needed before the capability arrived, not afterwards. A scientist arguing for limits on his own field is a signal worth reading. Chile is not alone. Similar legislative efforts are underway in Spain, whose National Digital Rights Charter names neurotechnology directly, and in Brazil, where state-level constitutional protection has already passed. In the United States, Colorado and California have both amended state privacy law to cover neural data. Different legal systems, different instruments, the same instinct. Write the protection down before the device arrives, rather than after the harm has already been done. The question has also reached the international bodies. Both UNESCO and the Council of Europe have taken up neurotechnology and human rights as standard-setting work. That matters for our purposes in one very specific way. When you tell an official that neural privacy is a serious subject, you are no longer raising something they have never heard of. You are pointing at a file already open on their desk. That is a different conversation entirely. So look carefully at the structure of that argument, because it is the model this series has been recommending throughout. It argues from demonstrated capability and funded programs. It reasons forward to what may become possible. It calls for precautionary law. And it does not assert that a covert brain-reading weapon has been built and deployed. That last restraint is precisely what makes the first 3 points so hard to dismiss. Which brings us to the synthesis. We have spent this episode taking the subject apart. Now put the pieces back on the table together, side by side, and weigh what each one actually carries. There are 3 of them. In the source literature, they are usually presented in a single confident voice, as though they were one thing. They are not one thing. Telling them apart is the whole method. Piece A is the real program. DARPA's Brain-Machine Interface Initiative, announced in 2002, matching Robert Asher's quoted claim from 2 months earlier. Its clearest fruit is the BrainGate clinical trial, implanted Utah arrays, published in Nature, repeated across laboratories. A paralyzed human being moved a prosthetic device with neural signals alone. Provided, and hold every word of this, they were surgically wired, extensively trained, actively cooperating, and physically tethered to a computer. Piece B is the funded reach. In 2008, the Army Research Office awarded a $4 million MURI grant across 3 universities, led by a real investigator named Michael Dzmura. The goal was decoding a willing wearer's own imagined speech through a non-invasive EEG cap. The grant was real. The research was published. The aim was a communication aid for a cooperating soldier or patient, not a surveillance device for an unwitting target. Piece C is the unproven claim. It is the mind weapon document's furthest language, echoed across the wider literature, associated with independent researcher Richard Alan Miller's brain transmitter theory, and with decades-old silent communication patents. It asserts that thought, emotion, and will can be transmitted between 2 people, covertly, without consent, at a distance. No public, peer-reviewed, or credibly documented demonstration of that capability exists. Here, plainly, the evidence runs out. 3 pieces, 3 different evidentiary weights, 1 document presenting them all in the same confident register. And note what that document itself concedes. The enabling nanotechnology has not yet been built. That is its own confession, not our skepticism. Absence of a published capability is not evidence of a hidden one. That inference is this genre's characteristic failure, and it is the trap we have spent 2 hours refusing to walk into. So separating them is not an act of doubt about the underlying subject. The technology is real. The trajectory is worth tracking. The neuroethical questions are urgent enough that one country has rewritten its constitution over them. Separating them is simply the only method that lets the documented pieces do their proper work of being believed, without dragging the unproven piece along for free. What that leaves us holding, we gather next. Chile's constitutional reform, the neurorights papers, the ethics conferences, all of that exists because the technology is real enough to legislate about. So we end where we began, with a document and a question. What did this episode actually establish? Not a verdict on anyone's experience. A method. 3 tiers, 3 different evidentiary words, and 1 honest measurement of the distance between a laboratory result and a claim about a stranger's mind. There are 3 things worth carrying out of this episode, and none of them is a conclusion about whether you personally are being targeted. The first is that a real memo described a real program. The second is that the same document outran its own science within a few pages. The third is the habit that protects you either way. Sort the claims rather than swallowing the whole thing or spitting it out. Start with what survives checking. The memo's author, Robert Asher, wrote in June of 2002 that the Defense Advanced Research Projects Agency, DARPA, had a brain-machine interface program. 2 months later, DARPA announced exactly that, publicly. Science Daily carried the story on the 20th of August. The claim that launched this whole investigation is independently verifiable. That matters. It means the document is not fabricated, and it earns a careful reading. And the clearest fruit of that funding is genuine. In July of 2006, the journal Nature published Hochberg and colleagues on a young man with tetraplegia who moved a computer cursor and a robotic hand by intention alone. That trial was called BrainGate. It is peer-reviewed, it has been repeated in laboratories since, and it is the strongest evidence this episode has. Tier 1 is not a rumor. It is published science. But notice what Tier 1 costs. That result required a 96-electrode silicon array, each shaft about 1 millimeter long, implanted through the skull into motor cortex by a neurosurgical team, in a consenting volunteer, followed by months of session-by-session calibration. Every demonstrated brain-machine interface in the published record needs invasive or contact hardware, a cooperating participant, and retraining. There is no version of this that works from across the street. What that hardware delivers is remarkable and narrow. Cursor movement, a robotic arm reaching for a bottle. More recently, decoded attempted speech in patients who cannot speak, again from electrodes resting on or in the cortex. These are motor commands, the brain's instructions to muscles, captured before the muscles fail. Decoding an instruction to move is not the same as reading a thought, and the researchers themselves are careful to say so. Set the two side by side and the difference stops being a matter of degree. The laboratory system is wired, consented, calibrated to one person, and limited to motor intention. The claim under examination is contactless, covert, uncalibrated, applied to an unwilling stranger, and concerns meaning rather than movement. Those are not near neighbors on one road. They differ on several separate axes at once, and every one of those axes is unsolved. That distance is the honest core of this episode. It is not a step. It is orders of magnitude on several dimensions at the same time, and no published result narrows it. Say that plainly whenever you describe this technology, because the plain version is the one that holds up when somebody checks it. Overstating the science does not strengthen a target's case. It hands the skeptic an easy exit, and they will take it. Tier 2 is the middle ground, and it is real too. In 2008, the Army funded a $4 million program in Imagine Speech, led at the University of California, Irvine, reported by the university that August and by the Associated Press. The knowledge base notes a RAND review listing synthetic telepathy among 7 potential capability sets. Funded is a real word. It means somebody paid. It does not mean anybody succeeded. Now the fault line. Within its own pages, that document slides from a decodable motor command to the transfer of, quote, emotional and volitional information between two people, and it never describes a mechanism for the harder half. It cites nothing for the leap. Lisa Feldman Barrett's work argues that emotions have no fixed neural fingerprint to decode in the first place. Here the evidence runs out and the text keeps walking. That is the one-voice knowledge base, not a critic, not a believer, describing the same distance in a single sentence. Direct contact sensors, extensive training, controlled environments. Remove any one of those 3 and the published results stop working. The remote claim removes all 3 at once. Hold that sentence in mind because it is the most compact, honest summary of Tier 1 that this series has been able to find. The documented chain is genuinely impressive, which is exactly why the exaggeration is unnecessary. 1969, Fetz trains monkeys to control single cortical neurons, in the journal Science. 1973, Vidal names the brain-computer interface. 1998, Kennedy and Bakke restore output from a paralyzed patient. 2000, Nicole Leese predicts hand trajectory from cortical ensembles. 2006, BrainGate. Every single one of those required electrodes in physical contact with living tissue. So here is the portable part, the vocabulary. Demonstrated means a named study in a named journal with a year and a result that others reproduced. Filed means a patent or a proposal exists. It proves paperwork, not a working device. Funded means money moved. Asserted means somebody said it. For words, for weights, and most confused arguments about this technology collapse the moment you insist on which one applies. Now the honest part, what we do not know. We do not know what sits inside classified programs, and this series will not pretend otherwise. We cannot prove a negative. But note the trap, because it is this genre's characteristic failure. Absence of published capability is not evidence of a hidden capability. A gap in the record is a gap. Treating it as proof turns an open question into a foregone conclusion. We also cannot explain every experience people report, and this episode has not tried. Nothing here tells you what is or is not happening to you. What it offers is language precise enough to survive scrutiny, so that the documented parts of your account are not thrown away alongside the parts that are not. That separation is protective. It is the whole difference between being questioned seriously and being dismissed. This matters for the record we are building together. One voice exists to turn scattered, easily dismissed testimony into a documented, evidence-led archive, and an archive is only ever as strong as its weakest citation. One overstated sentence lets a skeptical journalist discard 9 sound ones. So we name institutions, confirm dates against independent reporting, and state gaps as gaps. It is slower. It is less dramatic. It is the version that survives a courtroom. If precision is the tool, the archive is where it gets used. One voice is at one.witisk.org, a knowledge base, a documented declaration, and a community that logs incidents in a form that can actually be cited. TITV streams around the clock at meet.witisk.org. Under Public, TITV. Bring your evidence, and bring your skepticism, and bring the tears. Both are welcome here. Everything asserted in this episode is traceable, and the references stand behind it. Hochberg and colleagues in Nature, 2006. Vidal, 1973. Fetz in Science, 1969. Kennedy and Bakke in Neuroreport. DARPA's own announcement, reported on the 20th of August, 2002. The University of California, Irvine, and the Associated Press coverage from 2008. Check them yourself. That invitation is the entire method in one line. Next time we take the flagship claim of Tier 3 and hold it to this standard. Part 15, Remote Neural Monitoring, Reading the Mind from a Distance. The assertion that a specific, unwitting person's thoughts can be read at a distance, in real time. We trace it back through the Aquay lawsuit, the agency-adjacent lore, and the satellite claims layered on top, asking one question. What has a citation and what has only ever had a name? Thank you for staying with a difficult subject, and for refusing the easy version of it in both directions. This has been Part 14 of Knowledge Targeting, compiled from the One Voice knowledge base. If this hour gave you a sharper way to say what is real and what is not yet proven, pass it on to somebody who needs it. Sort the claims. Name the tier. And we will see you next time.